Hello everybody, I'd like to present the factorial ANOVA and more specifically the three-way ANOVA, the 2 by 2 by 2 balanced design. In this design we have three factors and each factor has two levels. And balanced design means simply that the observations in each group is the same. This is the question. What we have in this table are data comes from three independent factors A, B, and C, and each of these three factors has two levels. What is needed is simply to conduct a three-way ANOVA on these data. Assume that the significant level is 0.05. Before starting the calculations, let's understand all the details of the question. Regarding the first factor, which is factor A, we have two levels for this factor, which are A1 and A2. So small a is equal to 2. Small a represent here number of levels for the first main factor, which is A. So we have A1 and we have here A2. For the second factor, which is factor B, again we have also two levels, which are B1 and B2. So small b represent the number of levels for factor B is equal to 2. This is B1 and this is B2. And for the third factor, which is factor C, again we have also two levels, which are C1 and C2. So small c, which represent number of levels for this factor, is equal to 2. And here we have C1 and here we have C2. Number of treatment groups or number of combinations, we have 8 groups, or simply we can multiply the level for factor A by the level of factor B by the level of factor C, and we get number of groups, which is 8. For example, this group here represent the group for A2, B1, C2, and we have 3 observations in this group, which are 6, 8, and 5. And the total of the observation for this group is 6 plus 8 plus 5, which is equal to 19. And number of observation, we have 3. Notice that all the 8 groups contain the same value of the small n, or number of observation, which is equal to 3. So number of observation each group, small n, is equal to 3. And for the total observation, we can simply calculate the capital N. We have 8 groups, and in each group we have 3 observations. So the total observation is simply 8 multiplied by 3, or 2 by 2 by 2 multiplied by 3, which is 24. 4. Let's make some simple calculations. This is the main table which contains the raw data. Again, for example, this group here is the group which is represented by A1, B1, C1, and we have 3 observations, and the 3 observations are 2 and the 3 and 5. So the total of the observations in this group is simply 10. So by summing up all the observations in each group by the same manner, we get the table here. For example, here the number 20 represents the total observation for the group A2, B2, C1. And the number 20 simply comes from the raw data in the above table, A2, B2, C1. These are the data. So if you make a simple calculation for the total, you will get a 20. Here we have the totals. This is the total of B1, and this is the total for B2. And we have 125 represent the total observations. We need to make records for each 2 factors in order to facilitate the calculation. For example, for the records for A and B, simply here we ignore the third factor, which is factor C. So, for example, this number here, which is 21 represent the group which contains A1 and B1. And A1, B1 from the main table here, A1, B1 is simply all of these details or observations. So the total here is 2, 3, and 5. We have 10, and 6, 3, 2. We have 11. So the total is 21. And number of observation for A1, B1 is equal to 3 in this group, and we have 3 observations in this group. So we have 6 observations. So as you notice here, we ignore C1 and ignore C2. For example, regarding the 42, for A2, B2 is simply all of these observations. So if you make a simple summation for these observations, you will get the value of 42. And number of observation for A2, B2 is 3 plus 3, we have 6. So the total of B1 is 64, the total for B2 is 61, the total for A1 is 40, while for A2 we have 85. By the same techniques, we can make the records for both 2 factors A and C. For example, let's say the 44 here, which is inside the cell A2 C1. If we return back to the main table, A2 C1 is simply all of these data by ignoring B1 and B2. So if you make a simple calculation for the sum, you will get 44, and number of observation for A2C1 is simply 3 here and 3 here, so we have 6 observations. And we have here the sum of C1 and the sum of C2. And also for B and C, for example, this value here, 31, is the value inside the cell B2 C1. So if we return back to the main table, B2 C1 is simply this value, and again here we have this value. So the total of these observation is simply 31, and the total observation or number of observation we have 6. And we have here the summation for both C and B. First of all, before starting the calculation, the first step is to state the hypothesis. Actually, in case of the three-way ANOVA, we have 7 sets of hypotheses, 3 sets for the 3 main factor and 4 for the combinations between these 3 factors. So for the first main factor, which is factor A, we have the null hypothesis, which states that the average or the mean for A1 is the same as the mean for A2, while the alternative hypothesis represents or states that a mu sub A1 is not the same as mu sub A2. They are different. For the second factor, factor B, again we have the null hypothesis, which states that mu for B1 is the same as mu for B2, and the alternative hypothesis states that they are not the same. For the third factor, factor C, again we have the null hypothesis. Mu for C1 is the same as mu for C2, while the alternative one is the opposite, which means that the two means are not the same. We have 4 interactions between the 3 factors. So the null hypothesis for the interaction is always state that there is no interaction, while for the alternative hypothesis it states that there is an interaction. For the 3 factors A, B, C, we have 4 combinations, which are AB, AC, BC, and ABC. So we need to test a 7 hypothesis for this question. This is the table for the 3-way ANOVA. The source of variation, we have 3 factors or 3 main factors. We have A and factor B and factor C, and we have 4 interactions between these three factors. We have between AB, between A and C, between B and C, and between all of the factors. Also, we need to calculate for the degree of freedom for all of these, and then we need to calculate for the SS, or the sum of squares. Then we need to calculate for the MS, or the mean square, and finally we can get the value of the statistic F, or the calculated F, and we will determine the value which is F critical. So first we need to calculate the degree of freedom. For factor A, we have two levels for this factor. So A is equal to 2. So the degree of freedom for this factor is A minus 1, which is 2 minus 1, which is equal to 1. For the second factor, factor B, the degree of freedom is simply B minus 1, which is 2 minus 1. And again, we have 1. For the third main factor, C, C minus 1 is equal to 2 minus 1, and it is the same, we have 1. Regarding the degree of freedom for the interaction, simply we multiply the degree of freedom for the combination of the interaction. For example, for the degree of freedom for A and B, we multiply the degree of freedom for A by the degree of freedom for B. So we have 1 times 1, so we have 1. For AC, degree of freedom, this is the degree of freedom for A, and this is the degree of freedom for C. So 1 times 1 is equal to 1. For B and C, the degree of freedom is B minus 1. This is the degree of freedom for the factor B. And this is C minus 1, the degree of freedom for factor C. So we have 1 times 1. We have 1. The degree of freedom for all the interactions between the three factors. We simply multiply the degree of freedom for factor A by the degree of freedom for factor B by the degree of freedom for factor C. So we have 1 times 1 times 1, so we have 1. Notice that all the calculated degree of freedom are 1s. Regarding the degree of freedom for the error, we can simply use this formula. We multiply A by B by C by small n minus 1. Small n here represent the observations, or number of observations in one group. A is equal to, B is equal to, C is equal to, n minus 1 is 3 minus 1, and the degree of freedom for the error is simply 16. Now we can simply calculate the degree of freedom for the total degree freedom. We can make simple summing of all of these degrees of freedom. So if you make a simple summation, you will get 23. Or simply you can use this formula, which is equal capital N minus 1. Capital N here represent the total observations in all the 8 groups. So we have 24 minus 1, which is 23. Simply we fill all the degree of freedom inside the three-way ANOVA table. Notice that all the degree of freedom for the main factor A, B, C and for the interactions between the three factors are ones. Only the degree of freedom for the error is 16. Now we need to calculate for the sum of squares, which is abbreviated by SS. Before the calculation of the SS, we need to calculate for the correction factor. The correction factor is needed to complete the calculation for the SS for all of the variables. The formula for the correction factor is a simple formula. The correction factor is equal to the summation of y squared divided by n. The summation of y represent here the total observations for all the 8 groups. So it's already calculated and it is 125. So we square the 125, and regarding to the capital N here represent the total number of observation, which is equal to 24. So we square the summation of the total observation and square it and divide it by the capital N, which is 24. So the value of the correction factor is simply 651.042. Notice that all the calculated values are listed here in this table. Now we need to calculate for the sum square total or the SS total. The formula for the SS total is a very simple formula. It's equal to the summation of the squared observations, all the observations squared, minus the correction factor, which has been calculated yet. The total of the squared of the observation, we square all of the observation inside the table, starting by 2 and 3 and 5, and ending by 9 and 5 and 8. You can simply use the Excel in order to facilitate this calculation. So the summation of the squared of all the observation is simply 785. So now we simply can calculate for the SS total. So this is the summation of y square, and this is the correction factor. So the value of the SS total is simply 133.958. Now we need to calculate the SS for the 3 factors separately. We start with the SS for the factor A or SSA. The formula to calculate the SS for factor A, simply we have 2 levels for A, which are A1 and A2. So we should have the summation for A1, and we square it, plus the summation of A2 and square it, and divide it by number of observations in one of A1 or A2 minus the correction factor. Regarding A1, this is A1, it's equal 40. And regarding A2, we have 85. So we square the 40 plus the square of 85 divided by 12. Let's understand how we get the value of 12, or simply 3 times 2 times 2. As we said here, this value, which is 12, represents the number of observations inside A1 or A2. They are the same. So let's calculate for A1. So if you return back to the main table here, A1 represent all of these data. And if you make the summation for all of these observations, you will get 40. What is the number of observations in these data? We have here 3, and here we have 3, and here we have 3, and here we have 3. So we have 12 observations with total of 40. So the 12 comes from multiplying 3, which is represent the n, times b times c. And finally, we subtract the correction factor. So if you proceed with the calculations, you will get the value of SSA to be 84.375. The same way, we calculate for the sum square for the second factor, which is factor B, which is SSB. Again, for factor B, we have two levels. We have B1 and B2. So we should have the summation of B1, and we should square it, plus the summation of B2 and square it, divided by the number of observations in B1 or B2. In both B1 and B2, they are the same. And finally, minus the correction factor. Regarding the summation of B1, here we have in this table the summation or the sum of B1, and here we have the sum of B2. So this is B1 squared, and this is 61 squared. And if you calculate simply for the number of observation, we say that number of observation is simply the number inside B1 or B2. Let's return back to the main table here in order to calculate or count for the number of observation, for example, in B1. The data which is related to B1 is all of these data. So the sum of all of these observations, you will get 64. What about the number of observations here? Here in this group we have 3, and here we have 3, 3, 3. So the number of observations for B1 is equal to 12. And the 12 simply comes from multiplying 3 by 2 by 2, which is n times A times C. You can use a routine in order to know the values you should multiply. Here we are calculating for SSB, for B. So we have N, and we have A, and we have B, and we have C. So we are calculating for B. So the rest is N multiplied by A multiplied by C. Or simply you can count from the main table as I have done. This is the correction factor. So if you proceed, you will get the value of the SSB, which is 0.375. Notice that the value of SSB is a little bit small, so the chance here in order to reject the null hypothesis is very little. For the SS for the third factor, which is factor C, the same way, we have two levels, C1 and C2. So we square both C1 and C2 and make the summation and divide it by number of observations inside C1 or inside C2. Notice they are the same. So for C1 is equal to 65, so we square the 65 plus C2, which is 60, divided by what is the number of observations for C1 or C2. Let's count the number of observation for C1, for example. Again, we return back to the main table. So C1 is simply include these observations and these observations. So if you make a simple summing up for all of these observations, you will get the value of C1, which is 65. So the number of observations, here we have 3, and here we have 3, and here we have 3, and here we have 3, so we have 12. You can use the technique. We are calculating for C, so the rest is N times A times B. N we have 3, and A is equal to 2, and B is equal to 2, so the result is 12. And this is the correction factor, so if you proceed, you will get the value of the SS for the third factor, which is factor C. It is 1.041. By this, we have finished all the SS for the main factors, A and B and C. Now we start the calculation for the SS for the interaction between these three factors and we start with the SS between factors A and B, which is SSAB. Notice that for the calculation of the SS for the interaction, first we should use this formula. For example, we need to calculate for SSAB. So first we have this unknown value, which is SS for the subtotals between A and B, minus SSA minus SSB. Both SSA and SSB have been calculated. So the unknown value is the SS for the subtotals A and B. Notice here we have 4 values for the combination between A and B. Simply they are A1B1 and A1B2 and A2B1 and A2B2. So regarding the calculation for the SS for the subtotal, we are interested in the records inside the cells or inside the groups separately. So this is A1B1, this is A1B2, A2B1, and A2B2. We square all of these values and then we divide it by the number of observation for one of these cells. And simply because we are calculate for the AB, the rest is N and C. So we multiply N times C. Or simply we can use the second routine. This is A1B1, 21 squared plus A1B2, 19 squared, A2B1 and A2B2 squared divided by 6, which is N times C. Let's count for the 6 in a simple way. Let's take, for example, the cell A1B1 from the main table. A1B1. A1B1 represent all of these observations. So if you count for all of these 6 observations, you will get 21. We have in the first group we have 10, and in the second group we have 11, so the total is 21. Regarding the number of observation inside these 2 groups, we have here 3 in the first group and we have 3 in the second group, so we have 6. So the value of the SS subtotal AB is 84.791. Now we can return back to the tab formula in order to calculate for the SS AB. This value represents the SS for the subtotal A and B. This is SSA. You can easily get it from the table in the corner. And this is SSB. So the value for the SS between factors A and B is simply 0.041. Notice that the chance for the rejection of the null hypothesis is very little because the value of SS is is very little. By the same way, for the sum square for factor A and C, which is SS AC, this is the formula to calculate for the SS between A and C. We have this value, which is unknown, and these values are known. How to calculate for the SS for the subtotal between A and C? We have 4 subtotals or 4 groups. We have here this group represent A1C1, and this group represent A1C2. This group represent A2C1, and this group represent A2C2. So we take this value, square it, and divide it by number of observations in one of these groups. And simply because we are calculating for AC, the remaining is N times B. This is A1C1 squared. This is A1C2, A2C1, and A2C2. And here we have 6, which is the total observations. Let's again count for the total observations from the main table. Let's say, for example, let's calculate it for A1C1. What is the meaning of A1C1? A1C1 represent all of these observations. Notice that we ignore both B1 and B2 in this process. So the total for A1C1 is simply 21. And number of observation, we have here 3, and here we have another 3. So the total observation or total number of observation is equal to 6. We proceed. This is the correction factor. So this is the value of the SS for the subtotal between A and C. It's 85.458. Now we can return back to the original formula in the above in order to calculate for the SS for AC. This is the SS for the subtotals A and C, and this is the SS for A, and this is the SS for the factor C. So the value of SS for factors for the two factors A and C is 0.042. The third interaction is between B and C. So to calculate the SS for B and C, we use the same procedures. We need to calculate first for this value. These two values are already known. For the combinations between B and C, we have 4. We have B1C1, we have B1C2, we have B2C1, and B2C2. This is B1C1 equal to 34. This is B1C2, it's equal 30. This is B2C1, it's 31, and this is B2C2 is equal to 30. So we square all of these 4 values and summing them, divided by the number of observation in one of these combinations. or simply because we are counting for B and C, the rest is N and A. So we multiply N times A, which is equal to 6. Another way to get the 6 is to count from the main table. Let's say, for example, let's take the B2 C2 combination. B2 C2. So B2 C2 contains these observations plus these observations. So the sum of B2 C2 is the sum of these 6 observations. So if you make simple summation, we have here 8, with 9 we have 17, 22, so we have 30. Regarding the number of observations for B2 C2, here we have 6, and here we have 3, and here we have 3, so both are 6. So 3 by 2 is equal to 6, and this is the correction factor. This is the value of the SS for the subtotals between B and C. So now we can calculate for SS of BC. This is SS for the subtotals BC. This is the SS for factor B, and this is the SS for factor C. So this is our final result for SSBC. It is 0.375. The rest here is to calculate the SS for all the factors, which is SS A and B and C. And in this case, we return back to the original table, but after summing up the observation inside each of the 8 groups. So we have 8 combinations here. For example, we have this value here, which represent group A1, B1, C1 with total observation of 10, and number of observation inside this cell is equal to 3. But before starting the calculation, this is the original formula. We should calculate first for the SS for the subtotals for both the 3 factors A, B, C. And all of these SS are already calculated. So we have here 8 combinations for the 3 factors A and B and C. We sum up all of these squared values and divide it by the small n. Small n here represent the number of observation inside one of the groups, which is equal to 3. Notice that we are calculating for ABC, so the rest is n, minus the correction factor. So we have here, this is A1, B1, C1 squared. This is A1, B1, C2 squared. This is A1, B2, C1, etc. Divided by 3, and this is the correction factor. So This is the value of the SS for the subtotals A and B and C. So now we can simply calculate for the SS for ABC. This is the SS for the subtotals between A, B, and C. And these are the values for the SS for all the combinations and the three factors separately. So the value for SS for ABC is equal to 5.042. Now the rest is to calculate for the SS for the error. Notice that we have calculated the SS total and we calculated all the SS for all the main factors and the combination. So simply the SS total is the total for the SS for the three factors separately plus the SS for the interactions between the three factors plus the SS for the error, which is unknown. So simply you can move all of the known values to the opposite side, so the sign will be opposite. So the SS for the error is simply SS total minus all of the SS for the main factors and the combination. So this is the value of the SS for the error. It is 42.667. We fill all of these values of SS inside the three-way ANOVA table. Now we need to calculate for the mean square or the MS. The formula for the calculation of the mean square is simply we divide the sum of squares by the degree of freedom. For example, for factor A, the mean square for factor A is simply we divide this value, the SS for factor A, by the degree of freedom for that factor. Notice that all the degree of freedom are ones. So the calculations here will be very simple. So for A, MS for A is equal to SS for A divided by the degree of freedom for factor A. This is the SS for A. You can take it from the table at the corner. And this is the degree of freedom. It's 1. So this is the mean square for factor A. The same procedure for B and C, and for the interactions between A and B, and A and C, and B and C, and between all the three factors. And we can calculate for the MS for the error. Notice that the degree of freedom for the error is 16. This is the SS for the error, and this is the degree of freedom for the error is 16. So the mean square for the error is 2.667. So we fill the values of the mean square inside the three-way ANOVA table. What is needed now is to calculate for the value of the statistic f. And the formula for the calculation of f is simply we divide the mean square by the needed factor by the mean square of the error. For example, in order to calculate for f for factor a, we divide this value, which is the mean square for factor a, divided by this value, which represent the mean square for the error. So this is the formula to calculate for the statistic f, or f calculated. F for a is equal to the mean square for a divided by the mean square of the error. This is the mean square for factor a, and this is the mean square for the error. And this is the value of f for factor a. Notice that the value of f for factor a is significantly great. So the chance to reject the null hypothesis is very big. The same way for b, we have this value for f for factor b, and this is for c. This is for the interaction between a and b, and this is for the interaction between a and c. This is for the interaction between b and c. This is for the interaction between the three factors. By this, we get all the value of the calculated f. The rest here, in order to complete filling the three-way ANOVA table, is to determine the value of the critical f. In order to determine the value of the f critical, we need to know three things. First, we need to know the value of the significant level, and in our question it is 0.05. And we need to know the degree of freedom for the numerator, or df1, which is the degree of freedom for the corresponding factor, and we should know the degree of freedom 2, which is the degree of freedom for the error. Notice that all the degree of freedom for the main factors and for the interactions are 1s. So all of these sources will have the same value of f critical. And the degree of freedom for the error is 16. So we can simply return back to one of the f distribution table for probability or significance of 0.05. So this table is related to the alpha of 0.05 in this row here, we need to know the value of the first degree of freedom. And as I have mentioned, all of the variables have a degree of freedom of 1. And for the second degree of freedom, it is the degree of freedom for the error, which is the 16. So the intersection between these two degrees of freedom is 4.49. So the value of f for probability of 0.05 and degree of freedom in the numerator equal to 1 and degree of freedom in the denominator, which is equal to 16, is simply 4.49. So we fill the value of the F critical inside the three-way ANOVA table. Now, in order to draw the conclusions, simply we should compare between the calculated value of F and the F critical. For example, for factor A, the value of the calculated F is 31.637. It is significantly bigger than the F critical. So for the factor A, we reject the null hypothesis, which states that the mean for A1 is the same as the mean for A2, which is simply we accept the alternative hypothesis, which means that the two means are not the same. For example, for the factor B, as you notice here, the value of the calculated F is less than the critical value of F. So for factor B, we accept the null hypothesis, which states that the mean for B1 is the same as the mean for B2. Notice for the rest, which are C and AB and AC and BC and ABC, all the F values are less than the F critical. So we have only for factor A, we have a significance at level 0.05, while the rest, we don't have any significance. So this is the conclusion. Only for factor A alone, the F calculated is greater than the critical one, which is 4.49 on level 0.05. So we reject the null hypothesis and accept the alternative one, which means that there is a significance, and simply this means that the mean, the value of the mean for A1 is not the same as the mean for A2. And regarding all the other main factors, which are factors B and C, and all the interactions are not significant, simply because the value of the calculated f is less than the value of the critical one. And for all of these, we accept the null hypothesis, which means that there is no interactions between the combination of the three factors, and again there is no significant for both factors b and factor c. That's all for the three-way ANOVA or factorial ANOVA 2 by 2 by 2. If you have any comments, please write it down. Don't forget to click for the like and don't miss the subscribing. Thank you.